Okay, let's get started and finish up. Thanks. Okay, so this is the last lecture of geometric optics. Don't woohoo too loudly. We will meet again in Hilary term for wave optics. So as I said yesterday, everything in this lecture is actually non-examinable, so, you know, sit back, relax, but just try and absorb a few things, which, I don't know, some things might be interesting, but as I said, this is stuff, nevertheless, that you are expected to know about, even if it's not examined. So I finished off yesterday, rather, starting to talk about pieces of practical optical equipment with more than one lens. So telescopes and microscopes specifically is what we're looking at. And I got through talking about, the idealized case of the so-called astronomical telescope. Let's see if I can go back. Yeah, so there's a diagram of it, sorry. And that was a sort of idealized case. And then what I was going to go on to was just talking about some practical issues that one needs to consider if you're actually going to build one of these things or actually use it in any realistic way. So I'd started off just with this first practicality, which is how you can use this this so-called Barlow lens, a diverging lens, to essentially increase your effective focal length. So it's a diverging lens. It takes the light rays coming in from the objective, diverges them a little bit, and so if you trace it back, you get this effective focal length that's longer than the real focal length of the objective. The reason for that is that you may recall that the magnification for a telescope goes as the focal length of the objective over the focal length of the eyepiece, and so you've replaced this essentially in the numerator by this effective focal length, so getting a better magnification but without making your telescope much more big and bulky and heavy and expensive. Okay, so another thing is the issue of the fact that, as we discussed in an astronomical telescope, your image is actually inverted. Go back to the ray tracing that we did on previous slides and you'll be able to see that. So that's fine usually for astronomical telescopes if you're looking at things in space, nebulae, planets, stars. But if you're looking at something on Earth, then you might not want things to look upside down. So there are typically two main ways to sort that out. One is the use of an inverting lens. So we saw how these worked actually back when we were first looking at ray tracing and lenses. So if I've got my objective here, my objective lens here, for example, we've got these parallel rays coming in. What you can do is let these converge. So this is the objective focal length there. And if you place another lens, two of its focal lengths away, then, so this is the inverting lens, what happens is that it will invert the image again, but not change its size. If you remember, sort of if you put it two focal lengths away, then it just has the effect of inverting. And then you have your eyepiece as usual, okay, like that. So, the minimum distance, as you will have shown in the problem sheet, or will be showing in the problem sheet, the minimum distance between an object, we're treating this as an object, it's really the image that's come from here, but anyway, it's a real image, treating that as the object for this lens, and then the real image is here. The minimum distance you can have between object and image is 4 focal lengths. So the problem with that, it works nicely, but the problem with that is that you have increased the length of your telescope again. So you may not want that, and so a better way is to actually use a system of mirrors. So it turns out that if you rather than using this lens, you reflect your light rays via 2 mirrors, and if you place those mirrors correctly, so axes at 90 degrees, you can actually cause a reflection that will flip the image back up again. It might be interesting for you to go away and sort of draw some diagrams to convince yourself of that. So for example, that's something that's used in binoculars. It's not actually mirrors here. It's a pair of what's called poro prisms, and these work on the basis of total internal reflection, so you can maybe see how this is working. And this has the advantage of that you've folded up the optical path length basically into a much shorter distance than the actual, if we just follow this red line round, much shorter distance than that actual length of the real optical path length. So it has so that's what's going on inside your binoculars if you've got any. So that's a very clever way of doing it without making your piece of equipment more bulky and longer. So another consideration is actually what size of objective lens do you actually need? So I'm returning to this picture here to discuss this on the exit pupil. So this is where all the rays are bundling up together. This is, as we mentioned yesterday, this is where you should put your eye to be able to view the whole field of view. So it turns out that what you want, roughly speaking, is that for the diameter of this exit pupil to be roughly equal to the diameter of the pupil of your eye. So that's what I mean by that. So what should I call it? EP and eye pupil, it's a bit annoying. So that's exit pupil, meaning that diameter there, and this is going to mean pupil of your eye, right? So write whatever you need to make that clear to yourselves. Okay, now why is that the case? Well, you'll show in the problem sheet that the diameter of the exit pupil is given by the diameter of the objective lens over the magnification. Okay, I could write that as DFE over F naught if I wanted to, but anyway, right. So this is the diameter of objective lens. Okay, so I'm going to use that a few times in these slides to come, so that's what that's going to mean always, not the near point as we were using the same symbol for yesterday. Okay, right, and the other thing is that the brightness of an image you're looking at goes roughly as d squared over the magnification squared. Right, why is that? Well, the brightness goes as basically as the area of your objective, so that's the diameter squared of your objective. There's some constants out here, of course. And then it goes as the inverse square of your magnification. If you imagine looking at a little patch on a planet or something like that, and you magnify it by factor 2, right, the same amount of light is spread over 4 times the area, right? So that's why it goes like that. So what that means is that so a lower magnification results in a larger exit pupil, right, and also a brighter image, right? So a lower magnification does that, but at some point, but that's only useful so far, because if you make the exit pupil larger and larger, at some point it's going to become larger than the pupil of your eye. So actually, at some point, your eye pupil is not going to get any more light rays anyway, and so the image isn't going to become any brighter. So basically, that's a kind of limit on what you want to do. There's some useful minimum magnification that's worth worrying about. Other than that, you don't actually get any gain for it because the light rays aren't entering your eye anyway. Okay. Conversely, if you have a larger magnification, then yes, you get a smaller exit pupil, but also fainter image, right? So at some point, there's a sort of limit on the maximum magnification you can get because the image is getting fainter and fainter and you won't be able to really see it. So it turns out that the right thing to do is what I've just set up there, to basically look for an exit pupil roughly, where was it up there? Roughly the same diameter as your pupil. Okay, so what does that actually mean? In practice, well, okay, so exit pupil, you want roughly the same as diameter of your eye pupil, which is given by D over M. Okay, so what diameter do you want for your objective? Something like that, right? So traditionally, again, it seems a little bit optimistic that most of our pupils are dilated to 7 millimeters, but traditionally that's the value that's taken. You must be in very dark conditions and probably quite young to have that. But anyway, so somewhere between 5 and 7 millimeters is typical in very dark conditions. So what that means, this is your rule of thumb, so that means that if I want to have a magnification of 100, something like that, I'm going to need a diameter of my objective, something like 70 centimeters across. So that, that starts getting quite large, the larger and larger magnification that you want. After that, you've just got to accept that your image is going to get less bright if you want a larger magnification. Okay, so what you tend to do is just build the biggest objective lens that you can, or that you can afford, that you dare, because there are real limits on how big you can make these lenses, and then just sort of accept the loss in brightness after that. Something else to consider is actually the position of the exit pupil. You might want to actually move it. So let's say you want to move it slightly closer to the eyepiece, for example, because it's a little bit hard to hold your eye steady, further back, let's say. So you can do that with the use of a so-called field lens. So here's this third lens. Is put in, the simplest thing to do is to put it in the common focal plane. So the effect that this has actually is just to bend the light. So here are my rays coming in. Let's look at the purple ones, for example. And they're all being focused onto this common focal plane at the same position. Now, if you remember back to the days of prisms, oh, I'm sorry, this is another D. This is now the deviation angle, right? Hopefully you can remember that formula, and this is not the same D as that. Deviation angle, D. What should I? Oh, well, you know, right? If you remember back to that, you know that if these light rays are hitting the same point on our prism, it's essentially like on our lens, sorry, it's essentially like a prism of a particular apex angle. And so all that's going to happen is that these light rays are all bent by the same amount. So this lens does not, if put in this position, it doesn't refocus anything, it just bends the light rays, and so you end up bundling the rays together at a different place, right? So you can control that a little bit. And specifically, the simplest thing to do is what I've drawn here, where you put it in the common focal plane. And if we go back to our normal thin lens formula, if we choose, let's choose the focal length of our field lens is going to be given by the sum of the reciprocals of the focal lengths of the objective and the eyepiece. If we choose that, which is what it says on the slide, then what we've basically done, if you compare it with this equation, what we're basically going to be doing is imaging the objective lens right onto the eyepiece, if we choose that particular value. So that's the simplest thing to do, and to sort of understand the way that it might work. Now, do we actually want to image it right onto the eyepiece? Probably not. So again, things inevitably get more complicated than this. You don't want to image it right onto the eyepiece because the eyepiece is there, right? And if the eyepiece is there, you can't actually stick your eye there. You want it a little bit behind. And then something else is that you might actually want to use this common focal plane to put some crosshairs or a graticule or something like that, so you don't want the field lens right there. And then the other thing is that if there's any sort of imperfections in the field lens, for a minute I thought it said half past, and I was getting worried that I'd taken up that much time, thought we're not going to finish. Right. So the other thing is that if there's any imperfections in the field lens, bits of dust, something like that, and there inevitably will be, then the problem is if you put it right in this focal plane, you will perfectly image those imperfections on top of the thing you actually want to look at. So you don't tend to do exactly what I've said here. But if you do, anything else more complicated, then either drawing or doing the calculations really does get extremely complex. And so, again, you throw a computer at it. So all real designs of practical instruments are done by computer programming these days. Okay, so another practicality, or more practicalities you have to consider are, for example, the effects of aberrations. So I've mentioned these a few times. These are things that arise, consequences that arise from the breakdown of the paraxial or the thin lens approximation in some way or other. So I'll talk a little bit about those just at the very end of this lecture. Something else which I'm not going to discuss in detail here, but which you should be aware of. This is something we'll talk about in a lot more detail in Hilary term, but it's the effects of diffraction. So diffraction is basically the bending of light, or spreading out of light when it passes beyond an obstruction. Now, the thing is, the effects of diffraction mean that you can never, ever, ever form a perfect point-like image. Instead of a point-like image, actually, you'll get some sort of spread out spot, with an angular size, well, I'll just call it theta for now, that goes like lambda over d, where d again now is it's the size of your aperture, so it's the objective lens in the context that we're talking about here. So once again, I'm returning to this. For what d means, right. Now, so what that means is that if you have an infinitely large objective lens, if you could build such a thing, then you would be fine and you'd be able to focus a point-like object down to a point-like image. But as it is, you can't. You always have these effects of diffraction limiting your practical usage. So again, it's a case of you make your objective lens as big as you can, as big as you dare, as big as you can afford, and then accept the losses after that. And there's a traditional rule of thumb, which just says that the practical limit of magnification until diffraction effects start to dominate is just kind of multiply roughly your objective diameter by about 60. Your objective diameter in inches, so sorry, this was done before metric. So if you have a standard like 4-inch telescope, you could expect to get a magnification of up to 240. After that, if someone were to try and sell you a 4-inch telescope with magnification larger than that, then run for the hills because they think that you don't know what you're talking about. It won't work. Okay. The other thing is if you're observing from the ground, which we all probably are given our budgets, you've got issues with temperature fluctuations which can distort your image. So the sort of well-known twinkling effect of stars, which is lovely, and we all think of stars doing that, is actually just due to temperature fluctuations in the atmosphere, in the air. So what would you do? Well, you'd either fly up into space, put your telescope there, like Hubble or something, or these days there's a very clever branch of optics. Was the question? Very clever branch of optics called adaptive optics, which is very difficult to do but extremely clever, where you essentially continuously deform the shape of your lens to try and counteract the distortions in the air. Okay, what about focusing these instruments? So anytime you think of how would I focus an instrument, you should think of what are the things I can actually move. For a telescope, certainly for an astronomical use telescope, you generally can't move the object. It is where it is, generally at infinity. You also can't move the objective lens. That tends to be fixed to the tube. So it's the eyepiece that one tends to move. And so if you've got a little home telescope or anything, or seen any telescopes, you'll know that it looks something like this. Here's the objective lens, and then there's maybe something like that with a little control knob or something like that. So that's the eyepiece, that's the objective. So it's this thing that you tend to be able to move backwards and forwards. Why do you want to do that? Because in general, if you're using it, certainly for astronomical purposes, your object is always at infinity. So why would you need to move this? Well, of course, you might want to be viewing something on Earth, so something maybe not quite as distant, so you'd need to adjust that a little bit. And also, even if there was only one kind of object, there's not one kind of user, right? Some people might be short-sighted and not be able to view the virtual image at infinity, so you need to be able to adjust this for individuals' eyesight. So you essentially have this the distance between objective and eyepiece as the sum of the focal lengths, like I said, but then adjusted corrections either for the observer or for the actual distance of the object you're really viewing. Okay, so briefly, another type of telescope you might come across is the Galilean telescope. So this, instead of two converging lenses, so we still have the converging objective here, but now the eyepiece is actually a diverging lens instead. The distance between them is still the sum of the focal lengths. It's just that for a diverging lens, you've got a negative focal length now. So that's why it sits in front of the focal plane. So why is this good? What you'll see is that if you follow some of these rays, look at the purple ones, for example, you'll see that now the image is the right way up. It's not inverted anymore. So the rays coming from below are still coming from below when it reaches the eye. So this was Galileo's great breakthrough. Well, So he's put his name to it. He may have invented it, but there is some cynics say that actually he just sort of bought one off a Dutch merchant and then put his name to it, and who knows, I don't know. But anyway, he made it very popular. He realised that there was a big market for this, from rich landowners wanting to survey their empires from their castles, and they wanted to see things the right way up. So he sold a lot of these, but there is a problem with them, and it's that where exactly would you put your eye to be able to see the full image? Whereas with the astronomical telescope, we had a nice bundling of all the rays together. Now we don't have that. The exit pupil is actually somewhere inside the telescope. So the way that you'd have to use one is just to move your eye around, right? You know, put your eye at the top or the bottom or in the middle, depending on exactly what you want to see. In those days, it wasn't really considered a big issue. These things were so new and fun anyway that people didn't mind. But now it is considered, you know, an appalling feature that no one would use these things really anymore. Except for one purpose, and that's, so I'll just briefly mention that, which is as a beam reshaper. So if you just want to change the width, you've got a parallel beam of light and you just want to change the width of that, you can use one of these lenses. So we've got a converging lens at the front, we've got a wider beam of light, we bring it in, not quite to a focus, and then we can put this diverging beam in the appropriate place to get the parallel beam of light out. If you want it the other way, you do it the other way. A torch, for example, you sort of make a narrow beam into a wider beam of light, so you just do it the other way. Now, of course, you can do this as well with an astronomical telescope, no problem with doing that. Objective, eyepiece, you've got your parallel beam of light. We've seen these diagrams yesterday, right? And of course, you can get your parallel beam of light out like that. And normally that's not an issue. Okay, you've got a slightly longer piece of equipment here. But the main thing is that if you have very intense light beams, which you may do, very intense lasers, very powerful lasers, then it turns out that the electric fields are so strong that you really do not want to bring them to a point. You'd get such an intense beam that it would basically rip the air apart, right? It would ionize the air. So this sort of thing is very useful, particularly if you're working with very strong light sources, very intense light sources. Okay, so that was refracting telescopes. We're going to talk now a little bit about reflecting telescopes. These are really what all serious telescopes are a kind of reflecting telescope rather than refracting these days. So the basic idea is relatively simple. We've got our tube again. This is now a converging mirror. It's bringing the light rays down to a focus here. Now you've got two choices at this point. You could do, if you wanted, so-called prime focus photography. So you could stick your photographic film or CCD chip here and take a picture, that's fine. But again, mostly you want to view it with the eye, so you'd have to let the rays diverge again, stick your eyepiece here, and then in this very simple example, an observer would sit here and view it, right? We'll talk about more practical designs in a minute. Because, okay, having the observer here is going to block out a lot of light, so not something you really want. So the important thing, I think, to just realise is that this is really very similar to an astronomical telescope, right? You've got the mirror here reflecting the light, but then from here onwards, if you look sort of backwards, it looks exactly like an astronomical telescope anyway. Okay, so why are these better? There's lots of advantages, actually. One thing is that it's a lot easier to make a large mirror than it is to make a large lens. A mirror just needs a front, essentially. A lens needs a front and a middle and a back, and the middle can get quite bulky and expensive and heavy. Something else we'll talk about in a minute is chromatic aberration. We've already mentioned this back, I think, in the first or second lecture. So it's an issue that comes from the fact that light of different wavelengths has different refractive indices, so you get this sort of coloured fringes. But if you're just reflecting at a mirror, then you get no chromatic aberration, at least not at the main mirror. And if you're doing prime focus photography, then you don't get any chromatic aberration at all. And then a final thing, well, maybe not final, but the third thing I'm pointing out anyway, is that you don't need transparent materials, which may not seem like an issue to you. We're used to visible light and glass is absolutely fine. But if you're wanting to work in the far infrared or X-rays or something like that, actually it's quite difficult to get materials that are transparent. So you don't need to worry about that with mirrors. The downside is this partial blocking of the aperture. It's not ideal, but it turns out not to be terrible, and we'll look at some practical designs where this is minimized in a minute. And as I said, essentially all large telescopes these days are some kind of reflecting design. So the big breakthrough was the idea of a secondary mirror. So rather than a lens, which I showed here, and the observer sitting here all getting in the way, here's the idea of the secondary mirror. So the simplest way to do this would just be to have a flat mirror. So this is still the converging mirror, and if left to its own devices, it would focus down over here somewhere. Right, but if you put a flat mirror, maybe something like half a focal length of the main mirror away from it, then of course it just gets reflected, and then you'd have your focus here, and you can put an eyepiece. You'd want it a little bit behind, but anyway, you put then an eyepiece there, and an observer could sit outside. So that's obviously much better for that reason, the much better place for an observer to sit out here rather than in here, blocking all the light. And also notice that what you've done is folded up the focal length into a much shorter length tube as well. So you've got the same performance in terms of focal length, but in a smaller object. Somehow you need to support this secondary mirror. So that's normally done by so-called guide wires. So you are blocking a little bit of light, but it's normally not a huge issue. One thing you may or may not know is that the typical picture of a star that you will have in your mind of the spikes and everything, that's actually just diffraction off the guide wires, right? So you wouldn't see those nice star-like features, or what we think of as star-like features, without the diffraction effects off the support structure. So the Newtonian telescope is a slightly cleverer design. So Newton realized that what you could do is put this mirror at an angle of 45 degrees and reflect the light out of the side. And if you let these rays sort of come almost to a focus and then put the mirror there, you can actually make that mirror extremely small, and so block out hardly any light. And so that was a big advantage of this. You've lost the advantage, though, largely of folding up the focal length, because you do, in order to make the mirror small, you want to let this come almost to a focus. But anyway, it depends what thing you care about most. The Gregorian telescope, yet another design. So now the flat mirror is replaced by another converging secondary mirror. So here the light's coming in, we're allowing it to come to a focus first and then go beyond, and then here sits another converging mirror, and then the light is brought to its final focus here with the observer again sitting outside here. So again, you've lost much of the advantage of folding up the focal length, but the purpose of this converging mirror is that you've now inverted the image effectively twice, so you end up in the end with an upright image, right? So this is again a good terrestrial telescope design. So lots of sort of bird spotting scopes and things tend to be based on this sort of design. But if what you care about is astronomy more, rather than looking at birds, then the Cassegrain or some sort of variant of the Cassegrain is what you want. So rather than a converging lens here, you've now got a diverging lens. So the purpose of this is much like the Barlow lens, works exactly like the Barlow lens really. So the light comes in, and now you've got this diverging, slightly diverging beam. Of course it needs to come to a focus still, but what you've done then is folded up a very long focal length in what is a relatively short structure. So you can get this much longer effective focal length and therefore a much better magnification. I think it's gone off the board now, but the magnification being the objective over the eyepiece. And again, focal length. And again, there's a problem in the problem sheet. I think it's the last or second to last one or something, that asks you to look at this and calculate what the effective focal length is for a particular kind of telescope, and you see how really large it can be and therefore the benefit. Okay, pause for a bit. Take a drink of water, because I'm now going to go on to microscopes very briefly. We're not going to spend a lot of time on microscopes. Any questions so far? Okay, so the microscope. Oh, no, you're right. Okay, so are you okay? Yeah, sorry, just to check. If you do have any questions, just let me know. Okay, so we're going to go on to the microscope now. So you can see from the diagram that it looks very much like an astronomical telescope. This is the objective lens, here is the eyepiece lens. The difference primarily comes in from how, well, what you want to do with them, really, right? So rather than looking at objects at infinity, we're now looking at small objects very close. In fact, the object, as we'll see in a minute, you basically place at or just outside the focal point of the objective. And so that changes a little bit how we analyse the problem, because of course it means we can't assume that our rays are coming in parallel like we were with the astronomical telescope. So what basically happens is that this objective brings these light rays to form a real image here, which is somewhat magnified, also inverted of course, but somewhat magnified. So note this object will have to be just outside the focal point of this lens, because we want it to produce a real and an enlarged image. And then what this lens is doing basically is acting just like a magnifying glass. So this observer is, so you can place this, make sure that this real image is placed one focal length away from the eyepiece lens. And so what this observer is seeing is basically a virtual enlarged image at infinity. Okay, so think of it that this lens is producing a real enlarged image, and we have one stage of magnification just from the objective. So what should I call it, MO or something, right? So this is a kind of linear magnification, and if you remember, well, just look at the similar triangles here, right? These triangles, hopefully, if you can't remember that anyway, hopefully you can just work it out from looking at this diagram. So that's the first stage of magnification, which gives us this. And then you've got this second sort of magnifying glass type stage of magnification given by d over the eyepiece focal length, right, as we learned about yesterday. I think that's on the next slide, yes. Sorry, I should have moved on to the next slide. So you multiply those together, basically. And again, there is a problem in the problem sheet that asks you to look at this a bit more and analyse it in a particular way. Okay. So what you'd want then to get the maximum magnification is a short eyepiece focal length. That's a feature of a microscope. And also, you also want a short objective focal length as well. You want both of these to be short. Why should the objective focal length be short? Well, that's because where you place this object, so this distance u, is roughly the focal length of the objective. So this u, if you were to approximate, it should roughly be equal to f0 anyway. Okay, so you want both of those to be short to get good magnification. As usual, I'm simplifying the issue. Real microscopes look a little bit more like this, usually with 3 lenses. What have we got here? This is called a tube lens in the middle. Hopefully I've written it somewhere. Can you see? I can't see that. Oh yeah, weak tube lens, there we are. Yeah, okay. So you can think about this so let's imagine you have placed your object basically at the focal point. That is kind of how you want to use these real microscopes. So what that means is that the rays are converted, roughly speaking, into parallel rays here. They hit the tube lens, which then itself forms this real and enlarged image. And then again, this eyepiece is being used as a magnifying glass exactly as it was before. So that distance is the focal length of the eyepiece, right? So the magnification then you get from the first stage, from the is equal to, probably written it up there. Oh, I have written it out there, so I don't need to. Right. The magnification now you get from the first stage, from the combination of these lenses, so from going from here to here, is now the ratio of the 2 focal lengths. Again, just do a little similar triangles exercise in your head, right? Look at that triangle, noting that this object is basically placed at the objective focal length, and then look at that triangle, because that is, of course, the tube lens focal length, right? So that's your first stage of magnification, and then you get the usual magnifying glass type stage of magnification as well. So the whole magnification is given by something like this, D over FE in this real practical case. So why do you want to do that at all? Why bother with this extra lens? Well, actually, it just means really that you can replace, you can get different magnifications if you want to, just by replacing the objective lens. It might be easier for you to think about this in another way. So what you can think of this as is that the objective lens, if you place this object at one focal length away from the objective, what's going to happen is that it's forming these parallel rays. And so what you can think of it as is that these two lenses, the tube and the eyepiece, right, which are positioned the sum of their focal lengths apart, right, hopefully you can see that. So these are just acting like a telescope, viewing a virtual object at infinity that was formed by the objective lens, right? So the objective forms these parallel rays, you can trace these back if you want to, and then this system is being used as a telescope to view it. That might be another way to think about it. And then what you can hopefully see, that if you think of it like that, then it means that you could replace this objective lens by different lenses, so they will have different focal lengths, and then you can sort of adjust the magnification in that way, whereas everything else in here remains fixed. Right? Okay. How do you focus such bits of equipment? Well, actually, for microscopes, pretty much everything tends to be fixed. So all of these lenses are just fixed to the tube. The objective is usually replaceable, right? Because I've just talked about that you can use different ones, but usually fixed in place. So what you have to do is just move the whole thing backwards and forwards until your object basically sits at the focal point where it should for this to work properly, right? Just be a bit careful not to bump your object with your microscope. Okay, so that was focusing. Right. So finally, I come to talk a little bit about aberrations. As I say, we're not going to do this in a lot of detail, but I just want to give you a flavour of what are the main aberrations, where they arise from, why we have to worry about them, and some ways in which you can mitigate them in real practical designs. So aberrations are things that we have been essentially ignoring throughout, except for the occasional time that I've just mentioned them. But they are things that arise from the breakdown of the paraxial and or the thin lens approximations, which we've been happily using throughout. Well, largely, there are some aberrations that are for a different reason, right? So I'll talk about them as well. Right, so the big three, the three that I'm going to mention, are so-called spherical aberration and coma, and these two do arise from the breakdown of the paraxial and thin lens approximations. And then there's another one I'm going to mention called chromatic aberration, which we've already talked about a little bit, arising from dispersion effects, right? The fact that light of different wavelengths have different refractive indices. Only lenses are affected by that. So again, another reason why reflecting telescopes are preferred. Lots of other minor issues, you know, you can read in books about various things people have to take care of, but these are really the big three. Okay, so spherical aberration first of all. So we have already, in a way, talked a little bit about this, because we've talked about the fact that while we've been using an approximation of all our mirrors, all our lenses being spherical, we've talked about the fact that actually that's not quite the right shape, and what we need is a parabola if what we want is, so for parallel beams coming in this time, we did it for sort of to create a parallel beam, but for parallel beams coming in, if we want all of these rays to be focused at the same place, a parabola is what we need, right? And we showed that and finished off the proof of that yesterday. However, we've been working with a sphere and spherical lenses, and so what we saw, so that's supposed to be a parabola, there's supposed to be a circle nestling inside, and what we see is that basically the further you get away from the small angle, the paraxial approximation, you get to these edges which are simply too curved, right? They're not the right shape, they are too curved to get this exact focusing. So that's what spherical aberration is, it's that effect. It's that if you go too far away from the axis, then you end up with this stronger focusing power, and so these rays are being focused somewhat before the others, right? And so instead of a real nice sharp image, you get this sort of slight blurring effect. So that's spherical aberration. So you can get around it by making non-spherical lenses and mirrors. So parabolas obviously work well in this way to get rid of spherical aberration. But we'll see in a minute, parabolas are not perfect either for their own reasons. The reason they're called aspheric, things that are not a sphere are called aspheric. Everything was sort of bunged into that terminology just because spherical lenses and mirrors were so much more common once upon a time because it was the easiest thing to make, so everything else is just aspheric, right? Okay, coma. Coma arises from rays that are not parallel to the axis, right? So what I drew there and what we have been drawing quite a lot are these rays parallel to the optic axis. But if you've got rays coming in like this, for example, then you find actually they don't all focus at the same point. They sort of tend to climb up the focal plane in some way, and you end up with this sort of slightly teardrop effect. So this caused great excitement at some point with people thinking that they had discovered something very exciting, an exciting comet or something. Actually, they'd just seen a star with a bad lens, right? So, but the problem here is that parabolic mirrors, for example, suffer greatly from coma. So even though it's the right shape for this situation, you can get rid of spherical aberration, actually they suffer very badly from coma. So the things that you would do to sort out spherical aberration tend to make coma worse and vice versa. So that's where your issues arise. So in real practical designs, what you tend to do, and we'll see some examples in a minute, just a picture, is make multiple lenses or multiple elements in any practical piece of equipment that introduce their own aberrations but are carefully shaped to sort of cancel each other out in some way. So that's what people tend to do. Chromatic aberration. Okay, we've seen this before, starting off when we talked about the prism. But here's this dispersion effect, right? So a single lens made of a particular type of glass is going to cause the bending of different wavelengths to be slightly different and therefore focus in different places. So blue is bent more than red, for example, and you see these coloured fringes in pictures. Right, so a way to at least mitigate that problem is to use a couple of lenses. Here's an example. So we've got one converging here and one diverging, and they're made of different types of glass as well. So slightly different refractive indices. They also have slightly different dispersion properties in general. So crown glass tends to have quite small dispersion. Flint glass tends to have slightly larger dispersion. And that, combined with different refractive indices, you can engineer it precisely to have the right shape and everything so that you can bring a couple of colours to focus at the same point. So here, for example, red and blue have this focusing at the same point. Green is slightly off, but it's close. You can do actually even better with things called apochromatic triplets, for example, where you can bring 3 colours exactly to focus, and maybe yellow wouldn't be quite right, but you sort of got to, you do your best. Right? So there's quite a lot of, complex thinking and design that goes into these things. Something else which is very nice and quite interesting is that if you wanted to, you can forget the lens shape altogether. Have something flat, but where the refractive index varies instead. So graded index or GRIN lens. So from Fermat, you can see how this must work. So we've got a higher refractive index in the middle here, smaller at the edge. So we've got the shortest geometric path here, but the light will travel slower here in the glass than it does up here, and you've got to exactly compensate, right, so that all of these light paths take the same amount of time. So these work very well if you can make them, but they're very difficult to make. You've got to control the variation of the refractive index very, very precisely. It's quite tricky to do. You may be interested to know, though, or maybe you know this already, I didn't before I started lecturing this, that actually your eye lens has graded index properties. So it is curved. It does have the typical lens shape that you'd expect. But you'd find if you sort of analyse the problem that the focusing power of your eye lens is much better than it should be purely based on its shape. So actually it has this graded index, it works largely on this graded index basis, and it does that by varying the protein composition throughout the eye lens. It's very extremely clever. Also, because these lenses are so good actually, that is why your eyes do not suffer from very many aberrations. Your eyes are actually a lot better than most of these lens setups that I've been talking about, and it's because they work largely on this basis. Okay, I'm not going to say much about this. This is just to show you the kind of complexity that people start getting into once you start trying to compensate for all the aberrations. So these are, so don't worry about these lines. This is just called a field stop. It's sort of a black plate with a hole that can prevent bits of light getting to the eyepiece that you might not want to. You know, for example, to reduce spherical aberration, you might want to stop the outside bits of the light getting there or something. So don't worry about that, but just look at all the lenses. So these are the sort of basic lenses we started with: a simple convex lens, a concave lens. Ramsden and Huygens came along and realized that two plano convex lenses would work a bit better. Kellner and Plossel decided to put in some achromatic doublets, and then just people started adding more lenses for the heck of it, seemingly, to try and cancel out these various aberrations. This one is a really super duper lens that you would find in very expensive, you know, amateur telescopes, but you know, it's sort of the ultimate eyepiece. Yeah. So you can see how complex it gets to try and deal with these issues of aberrations in real pieces of equipment. Okay, nearly at the end. I think we're going to be just about nicely on time, hopefully. So I just want to show a picture of this, the Schmidt-Cassegrain telescope. So this particular telescope, the reason I'm showing it is because this is the best telescope we have here in the department, and you are able to go and visit that, I think, if you arrange with the secretary in astronomy. So it's a Schmidt-Cassegrain design. But it works with spherical mirrors. So both the main mirror and the secondary mirror are spherical, so it is very susceptible, that means, to spherical aberration. Where the Schmidt comes in is that what you do is put a sort of Schmidt, called a Schmidt corrector plate, which has a focal length of infinity, so it doesn't actually do any refocusing, but it's just carefully shaped to try and correct and cancel out the aberrations that come from the spherical mirrors in the first place. So, so about 20 years ago or so, this was the sort of design that any serious telescope, so it's serious amateur telescopes, I suppose, would have used, because it's a reasonably cheap way of correcting spherical aberrations. The spherical mirrors are easy to make, and then you just sort of try and do one cheapish, thinnish lens to sort of correct the worst aberrations. So that's a very popular amateur system, maybe a little bit out of date now, but it certainly was about 20 years ago. If you really, really are serious though, and you want to do, you know, want to get the best telescope you can, you would use a Ritchie-Chrétien telescope. So this is a Cassegrain design as well, but it's got hyperbolic mirrors. So that kind of gives you a best compromise between spherical aberration and coma. So Hubble is this sort of design, his Hubble. Hyperbolic mirrors in the days when Hubble was built, so it was, you know, put into space in the 1990s, they were very difficult to make, hyperbolic mirrors, and also quite difficult to test as well. So of course millions of dollars and a lot of time was spent carefully grinding the mirrors and carefully grinding them incorrectly, so that Hubble had absolutely terrible aberrations when it first went up. You may well have heard of this. Well, how did they correct that? Well, in the usual way, they flew up a pair of glasses for it, basically, a pair of spectacles, and essentially a corrector plate, right? So they flew it up, they installed it, and since then Hubble has worked extremely well indeed. So that brings us to the end of the lecture. Optics, you know, telescopes are there so we can do beautiful things, and optics allows us to do very important and beautiful physics. Thank you.